Alright, hello everybody, and today we're going to be taking a look at the derivative of x cubed. And remember, what is the derivative? Well, it just tells us the gradient of whatever function we have right here. So we have this derivative operator here, which basically tells us take the derivative with respect to our variable x of whatever we have in front of here, which is x cubed in this case. And remember, to find the gradient of a function, we can always go back to our best friend first principles, which says that the limit as h approaches 0 of f of x plus h minus f of x over h. And remember, we have the limit here because we want an accurate gradient that is tangent to our curve. And this numerator here is just the difference in the y value, so the rise, and we have the run on the denominator right here. So our function in this case is just f of x equals to x cubed. And if we want to find the derivative of our function, so remember this, the derivative operator just says find the derivative of f of x with respect to x. That's just equal to, well, all we have to do is substitute our function into our first principle. So the derivative of f of x is just the limit as h approaches 0. And you see f of x here, it's taking in x as an input and just cubing it. So if we have x plus h as an input, all we do is take x plus h and then cube it. And then we subtract the function itself, which is x cubed, and divide all that by h. Alright, and here comes the boring part. We have to expand out this x plus h all cubed. You can take out a piece of paper and try it out for yourself, just expanding it and everything. But let's just do it quickly on the board here. So we have limit as h approaches 0 of so collecting like terms to get the limit as h approaches 0, because we don't want an approximation, we want the actual tangent. X cubed and negative x cubed will cancel. Alright, and you see we end up with this expression right here. So I'm going to rub out some of this stuff up here so we have a little bit more space to work with. So you may notice that we have a common factor of h on the denominator, so why not factor it out? So now we have the limit as h approaches 0 of h times 3x squared plus 3hx plus h squared. And all of that is being divided through by h, so now we can cancel. And now we have the limit as h approaches 0 of 3x squared plus 3hx plus h squared. And this will tell us the gradient at every single point on our function x cubed. But at the moment, this is just an approximation because we haven't let our h go to 0 yet. So to get a final result, all you have to do is see what happens as these two h's here get smaller and smaller and smaller. Well, as these two terms here get smaller and smaller as h goes to 0, they're just going to literally just disappear. They're going to be so incredibly insignificant that we can just forget about it. So after we let our h approach 0, all that's left is 3x squared. And 3x squared is in fact our derivative of x cubed. So let me just put that over here. The derivative of x cubed is exactly 3x squared, as we found using first principles here. So now to kind of convince you that the derivative of x cubed is really 3x squared, let's draw up two graphs. So we have a graph of x cubed, which is just a cubic, like so, and then we have 3x squared, which is just a skinny version of a parabola. Alright, so let's analyze the gradient of our x cubed here, and I should probably write down the function x cubed and 3x squared. So as you can see here, if you look at the gradient along our x cubed graph, it's positive, it's positive, it's positive, it's positive, it's positive, it's positive. And right at the origin here, we have a stationary point where our gradient is 0. So what our x cube is doing is it's increasing, it's slowing down, and it stops. And then what it's going to do is it's going to keep going, and it's going to keep increasing with a positive gradient. And how is all of this stuff represented on our 3x squared, or the derivative of our x cubed here? Well, notice that if we plug in negative values of x, we're going to get values in the positive region of our 3x squared. And you can clearly see that the more negative we go on our x cubed, the steeper the gradient is. That corresponds to a bigger value on our 3x squared graph. And as we get closer to the origin, the value of the gradient on our derivative kind of gets closer to 0. And once it's at 0, well, we're expecting the gradient to be 0. So on our derivative graph, that corresponds to the y value at x equal to 0 being exactly 0. And how about if we go onto the right hand side? Well, notice that the gradient is also positive. That corresponds to the value of our derivative being positive on the positive side of our graph. So you can see here the derivative of x cubed is always positive except for when x is 0, where the derivative is just 0. So we're going to do another example of the derivative using first principles. We're going to let some function f of x equal to x, and that's just a simple straight line through the origin like so. And we're going to use first principles to find the derivative of x. So let's use some more derivative notation. Remember from last video that if we have f prime like this of f, this is saying take the derivative of our original function x. And to find the derivative, we can just use first principles, which is the limit as h approaches 0 of f of x plus h minus f of x over h. And well, f of x is just x, so whatever input we put into our function, we're just going to get the same output. So this becomes the limits as h approaches 0. We're plugging in x plus h here, so what we get out the end from our function is just x plus h. And then we're subtracting f of x, but f of x is just x, and we're dividing everything through by h. Alright, notice that this x and this negative x will cancel, and we're going to have the limit as h approaches 0 of h over h. But notice, h over h is just 1, so we have the limit as h approaches 0 of 1. But in this expression right here, there's no mention of h, so this limit here is redundant because we don't have any h here. We've only got this value of 1. So what we found out is f prime of x is equal to 1, and we can rewrite this a little bit as being the derivative of x is exactly 1. And that kind of makes sense because if you look at our graph x, like so, what is the gradient at every single point on our line here? Well, it's just 1. And I'm going to do a little something weird right here. I hope you agree with me that 1 is exactly 1 times 1. But what is 1? 1 is also x to the 0th power, because anything to the 0th power is just 1. And why did I do that? Well, we're going to find some kind of pattern right now. So we just found at the start of the video that the derivative of x cubed is 3x squared. In a previous video, we found that the derivative of x squared is exactly 2x, but I'm going to write that as 2x to the first power. And we just found that the derivative of x is equal to 1 times x to the 0th power. And I hope you can see some kinds of pattern here. If we take the derivative of x cubed, we have this 3 here that appears right in front of our x here, but the power reduces by 1. And similar for the x here, we have a power of 2. We're taking the derivative of x to the power of 2. That 2 appears right here, and the power reduces by 1. And if we take the derivative of x to the first power here, well, that 1 appears here, and our power reduces by 1 to make 0. So we can kind of generalize a rule for this to say that dx, so the derivative of x to any power n, is exactly, well, notice that the power kind of jumps down here to become n, and then we have x, and then the power of our derivative reduces by 1. And this is what we refer to as the power rule for the derivative. So we can either use first principles here to find, let's say, the derivative of x to the 8th power, which will take us who knows how long, Or alternatively, we can use the power rule to say that the derivative of x to the 8 is exactly 8 times x to the 8 minus 1, which is 7. So we can use this function right here to describe the gradient at every single point of our original function right here. So that's pretty cool. We found a new rule that we can use to find the derivative of x to any power. So that's pretty much the result for today's video. In the next video, we're going to muck around with some more derivative rules. But yeah, until next time, I'll see everyone later.